We surround ourselves with wheels on office chairs, medical carts, and delivery dollies. Most of the time, we treat them as simple, monolithic objects, hardware that we only notice when it suddenly locks up or drags a permanent scratch across the floor. Look at the bottom of standard office furniture, and you'll see small mobility devices that are almost universally referred to as wheels. Technically, the wheel is only one component in this assembly, the caster. To move a load, the wheel must be integrated with a mounting stem to connect to the furniture, a fork to hold the axle, and internal bearings to facilitate the swivel motion. The importance of that anatomy is clear when you look at a floor glide. It utilizes the exact same mounting stem and housing as a caster, but it is built to stabilize an object and prevent movement entirely. This explains why human intuition often fails during a hardware repair. We choose these devices based on visual simplicity, even though mobility is a problem of mechanical physics and environmental resistance. The physics of the caster begins at the contact patch. This is the microscopic area where the tread material meets the floor, and the two surfaces begin a continuous negotiation over friction. While it seems intuitive to match materials, soft on soft or hard on hard, the mechanics demand the opposite. Pushing a heavy cart across plush carpet requires hard nylon wheels to prevent the load from sinking. Conversely, rolling over hard tile or wood requires soft rubber or polyurethane to absorb vibrations and grip the surface without causing scuffs. Because soft rubber dampens sound and provides a smooth ride, it creates the sensory illusion of being the easiest material to move. This visualization shows the energy required to move these materials. Under heavy load, rubber deforms, increasing roll resistance and requiring more kinetic force. Size also dictates performance. A larger diameter wheel hits obstacles with less resistance than a small wheel, using a fraction of the energy. Efficient rolling is the result of mathematically matching the density and diameter of the wheel to the specific resistance of the floor. Moving a load horizontally is one challenge, but the engineering changes when we consider vertical stress, the weight pushing straight down into the axle. Twin-wheel casters are common because they distribute light weight over a wider area. But in heavy-duty industrial settings, complexity is a weakness. Single-wheel casters use a solid, continuous construction that can shoulder thousands of pounds that would cause a dual-wheel assembly to buckle. To allow these heavy loads to steer, industrial casters often rely on a thick central bolt called a kingpin to hold the swivel mechanism together. This cross-section shows the bolt's fatal flaw. Under lateral shock, it concentrates kinetic energy and fails. The kingpinless solution replaces the bolt with an interlocking raceway of steel ball bearings, safely distributing shock force around the entire diameter. Mechanical strength is not found in the thickness of a single anchor, but in how effectively the design can distribute stress through the entire system. Once a load is in motion, the physics shift again, this time to the mechanics of steering and stopping. To make a heavy cart maneuverable in a narrow warehouse aisle, the standard assumption is that you need swivel casters on all four corners. This layout shows a more precise alternative, the diamond arrangement. By using 4 rigid casters and mounting the center pairs slightly higher than the ends, the cart gains a central fulcrum. This allows a massive piece of equipment to pivot 360 degrees within its own footprint. Control also means being able to stop. While a standard brake is designed to halt a rolling object, some tasks require the opposite function. This is a reverse lock. The mechanism is engineered to freeze the wheel the exact moment a person sits down or weight is applied. It prevents the equipment from shifting during use and only releases to roll freely when the load is removed. Achieving control over heavy objects often requires engineering solutions that function in direct opposition to our natural instincts. In every hospital and warehouse, the movement of the entire facility depends on these microscopic physical interactions. The caster is the foundational element that dictates the lifespan of a building's floors and the mechanical integrity of the machines they carry. There is a direct ergonomic cost as well. The angle of a worker's spine and the physical fatigue they experience are determined by the rolling resistance and the swivel efficiency of the hardware beneath the load. Smooth, effortless movement is the output of a specific mechanical calculation. It happens when the wheel diameter, tread density, and swivel geometry are precisely tuned to cancel out the friction of the environment.